Here you go. Good morning. My name is Ingolf Steinbach. I work for Jena Optronic in Germany as a software system engineer. So my talk today is about failure detection, isolation, and recovery, response, or whatever you want to fill in for the R in the ASTRO APS Star Tracker. Star Tracker, our flagship Star Tracker product in the Jena Optronic company. Don't worry, I also want to be at home for Christmas, so I won't give a comprehensive overview of all the FDIR. I will concentrate on two aspects, which might also be understood as some follow-up to the previous speaker. We deal with hardware which is degrading gradually, and this will be the topic of my talk today. I'd also like to acknowledge the work by my co-worker, Dr. Uwe Schmidt, who is the chief system engineer for all of our Star Tracker products in the company. He has contributed the research for the algorithm, which I'll present in the second part of my talk. Please allow me a few words about our company. We deal with sensors for attitude and orbit control systems. That is Star Trackers for sure. This goes back to the 1980s, where we built the first Star Trackers. We have also other sensors, like, for instance, for automatic approach and docking of space vehicles. These are used, for instance, in transport vehicles to the International Space Station. And finally, sun sensors, which are also part of that attitude and orbit control system sensors which we are building. Furthermore, there is a second branch dealing with optical instruments, remote sensing, but I'll concentrate for sure now on the Star Trackers. If you have a chance to go to Germany one time, just give me a call. I'll be glad to give you an introduction to the company. And when you look at the map on the left side, you see that blue globe. This is where we live. So it's when you go from Berlin to Munich, stop after the first third of that travel, and then you will be in Jena. I'm pretty sure most of you know how a Star Tracker in general works. If you don't worry, it's not so complicated. The Star Tracker is typically mounted on the spacecraft and looks into the sky. It sees a few stars. So this is a circular field of view. So part of these stars can be seen by the Star Tracker. The Star Tracker tries to identify that star pattern using a built-in onboard catalog of known stars. From that identification, it then can derive attitude information, which is delivered to attitude control after that. And so this is more or less all the Star Tracker has to do. Unfortunately, it's not that easy. There are a few obstacles which we have to overcome. Some of these I'll present later. So these are the two topics. The first part is related to a change which we did in the storage, especially non-volatile storage in the Star Tracker, and the second one is related to the image sensor which is in the Star Tracker. Let's come to the change in non-volatile storage first. We replaced at some point in time our non-volatile storage, at least part of that. Replaced the PROM-only variant by a mixed variant using also EEPROM. The heritage we had from a predecessor, which is called ASTRO 15, was that customers disapproved of using EEPROM especially for geo missions. And so that predecessor, ASTRO 15, was just using PROMs as non-volatile storage. You can imagine that the customer had some worries about using EEPROM because EEPROM can lead to data loss if you have a strong radiation environment, for instance, or hot temperatures. Then you have to consider aging, where the EEPROM loses the data over time. And then, for sure, there can also be software errors or hardware errors in the system, which might lead to data loss. So the fear of our customers were that they were flying just an expensive brick on their satellite. Well, that might still be useful. We heard about planetary defense missions, so that brick could be used as, but typically your intention to use a star tracker is something different than that. So the first variants of the ASTRO APS star tracker also had this PROM-only approach. We had 256 kilobytes of PROM, which included a bootloader and also the star tracker application. And in addition to that, 8 kilobyte of unit-specific calibration data, which was integrated at a later stage after doing some calibration campaign. We were able to upload patches, but of course, as we did not have mutable, non-volatile storage, these patches always were volatile. As soon as you did a power cycle, these patches had to be reloaded again. So the pros, on the one hand, of course, are we have a reliable storage also in harsh environments and also good long-term stability. The cons, well, we can only do a very limited amount of software patches. And furthermore, the PROM storage itself, the parts are quite expensive. And then we had new customers with other different requirements, especially also for LEO missions, where you typically have shorter mission durations, and these customers required that they be able to completely exchange the application which is running in the star tracker. So we adjusted our hardware design to these new requirements, and now you can install any application in the star tracker even after launch. Any application does not necessarily mean you have a different program within that, but also you can also exchange the star catalog. For instance, when you have a very long mission, you might want to adjust your catalog at some point in time. This can also be easily done. Any application, of course, does not mean that you run your latest first-person shooter on that, but if you really find nostalgic, you might want to port and upload some ASCII game from the 1970s or 80s. But that's not our normal intention for this mechanism. Unfortunately, we now have a very limited data retention time. The EEPROMs we are using have a specified data retention time of some 16 years. That might not be so critical for a 7 or 8 year LEO mission, but if you have a geo satellite which is in orbit 15 years or longer, then this limited data retention can be critical. Also, you can imagine we had quite a lot of new, additional, and sometimes also interesting failure modes to be considered in the software. And if we don't handle these failures well, we might indeed lose the complete star tracker. So there was a need for an elaborate FDIR concept. Well, that's easy. Just put in a few more EEPROMs, put in some selection logic into the bootloader, and you're done. On day one, we had a talk of someone, I don't recall who it was, saying that it's easy to negotiate a few more watts. That's probably sure when you deal with a complete spacecraft. If you're a star tracker supplier, that's not so easy. For a star tracker supplier, power consumption, size, and mass, all these do matter. because if we exceed the usual values for that, then the product becomes more unattractive to a potential customer. So we ask ourselves if it's possible to have sufficient reliability in the star tracker without having redundant double EEPROM. So let's recall some of these new failure modes. I intentionally say new failure modes because there are a lot of additional ones which are generally related to a non-volatile storage or to hardware at all. These are some which come into view during this replacement of PROM-only storage with double EEPROM. So you can have this corruption of the double EEPROM content due to the limited data retention. You have corruption due to radiation, corruption due to software or hardware problems, or also when you do an update of the double EEPROM, some of the cells might not be correctly updated due to failures in the part itself. And something which we did not have on the previous slides, there might also be user errors. Think of the poor person in mission control who hits the wrong button and uploads something to the double EEPROM instead of the RAM. I'm sure you have safety measures to avoid that, but from the point of view of the star tracker, this is also a failure mode, and we should also take this into account. Or someone really uploaded a tic-tac-toe game inadvertently. Fortunately, the answer to the previous question is yes, we can find a robust solution without using this redundant double EEPROM. This solution comprises several measures. The first one, you all know, the best FDIR you can do is having a good design which makes a certain failure detection and after that recovery unnecessary. So we try to avoid potential failures before they can occur at all. One of these measures is that we retain essential functionality, vital functionality for the star tracker in PROM. That means the bootloader is located in PROM, and also I'll later come back to that and some fallback application. The second point is that we never ever execute directly code within the E2PROM. Also at runtime we don't use any data from the double EEPROM. Instead, the bootloader always copies during boot the image from the double EEPROM to an EDAC protected RAM, and only this runtime copy in RAM is then executed. And this protects against malfunction of the star tracker in case we have a gradually degrading double EEPROM. That cannot use to traps or any other malfunction in the star tracker. To continue on that, the double EEPROM itself comes with a built-in hardware protection against inadvertent writes. So this is activated by default. It's always on except for the very short moment where we are intentionally going to reprogram parts of that double EEPROM. And also in that case, the write protection is dropped only for one page within the double EEPROM. So when we do rewriting, only a very small window within the double EEPROM is temporarily not write protected. And then as additional measure, we have software write protection in place before you can perform any modification of the double EEPROM. You have to arm that command first. So this protects against this user error, which uploads something to the wrong place in the star tracker. Only after performing this arming command, you may then do some memory upload to the double EEPROM, and after a specified amount of time, this software write protection is raised again. The second measure is that we introduce a recovery application, that's some fallback mechanism in case something goes wrong during the booting process. We start an application which allows us to still communicate with the star tracker. It uses the same communication protocol as the nominal application, so you don't have to implement something specific for that situation. You can perform all sorts of maintenance activity, memory upload, self-test, and so on. So the bootloader performs checking of the EEPROM based on CRC values, which are stored in the EEPROM. And if anything goes wrong, this is the, where's the mouse? This is this branch here. The bootloader does not start the nominal application or copy the nominal application from the EEPROM, but instead copies this recovery application, which is also stored in PROM, to the RAM where it's then executed. And so even if you have a corrupted EEPROM image, you can still boot the star tracker, communicate with the star tracker, and then try and rescue that. In order to find out about this gradually degenerating EEPROM, we perform a continuous monitoring of the EEPROM image. This works as follows. We have a certain area reserved within our RAM, which holds a reference copy of the complete EEPROM image. This image is installed during cold boot by the bootloader. And within each of the star tracker cycles, we take one of the EEPROM cells, read that cell 4 times in a row, and compare those values which we have read from the EEPROM with the value which is located in the associated part of the reference image in RAM. So if all those 5 reads deliver the same value, we say that cell is correct. And in the follow-up cycle, we then advance to the next cell. If anything is wrong, like in this case where one of the reads of the EEPROM led to a different value, we raise an error flag and log that failed address. So you can then perform after that actions to deal with that situation. This mechanism goes through the complete EEPROM image within less than 15 hours. So you have quite a short feedback time. This is more than enough because, as you remember, we don't use that EEPROM during the runtime. We just use it at boot time. So as long as you don't reboot in between, you don't have any problems in this case. We deliberately don't perform any automatic correction activity here. That is because we cannot be sure that we are in a safe environment during that correction. For instance, during a solar storm, we would not do some EEPROM reprogramming. So only at the next reboot, this situation with a modified or unintentionally modified EEPROM image would lead to the bootloader deciding to boot that recovery application instead of the nominal application, but you are now still in a situation that you can recover from that error. This is the fourth measure. You have a few options to deal with that. Either you can copy the complete reference image back to the EEPROM. This can be done in parallel to the normal tracking mode, so you don't lose star tracker functionality in this using this method. Or you can decide to selectively try and reprogram the failed EEPROM cells via memory upload. And furthermore, the storage of the application and the EEPROM is partitioned in several segments. And we also store an application descriptor within the EEPROM, which for each of these sections defines where in the image this section is stored and where it is to be placed in the runtime image. So we can, by modifying this EEPROM image, we can place in the same application but with a different usage of EEPROM cells and avoid damaged cells in that way. And the fifth measure is that we have the concept of a test application. The bootloader is not only able to start the nominal application from the EEPROM or that recovery application from PROM, but it can also boot the reference image which is stored in the RAM. So when you do some modification of the software, you can upload that modified image first to that RAM copy. You don't have to directly alter the EEPROM, and because it's in the RAM copy, you can, by power cycling, for instance, you can restore the previous state of the start tracker quite easily. Then you boot that modified image from the RAM, do some basic checks, for instance, whether you can still speak with the start tracker, whether everything works as expected, and only after those successful checks, you copy back that modified RAM image to the EEPROM. So this, as I said, protects against having this expensive brick here. So our results is we have nearly PROM-like reliability, for sure increased flexibility with respect to the PROM-only variant. It's really foolproof, I think. You have to really perform some severe bad will actions to circumvent this mechanism. And we need only very small PROM capacity, which saves us cost, printed circuit board space, and also power consumption. And as we only need one EEPROM image with one application image, this again saves cost and space and power consumption. By the way, the RAM was already big enough to hold this reference image, so we didn't need to enlarge the RAM for this. Some of you were here last year, but please forgive me that I show the same image as last year here. It's one of my favorites. You see the size of the start tracker. The side length is less than the size of $1 bill. So this gives an impression of the size of the start tracker. The second part of my talk is related to the image sensor, where we have to deal with degrading pixels. The ASTRO APS has a built-in APS image sensor, and these APS image sensors have some characteristics which I'll present in a few moments. First thing which is necessary to recall is that we are looking at the celestial sphere. That means we have a very, very low signal-to-noise ratio here. The star light is quite dim, and often you cannot, by looking at an image as a human, you cannot really distinguish that star image from the background noise which we have on the detector, at least for faint stars. These APS sensors have a few disturbances, or come with a few disturbances. Some are quite prominent, white spots, for instance. Some are not so prominent, but especially when you compare that disturbances with the signal of your star image itself, these still might lead to degradation in star measurement. You can see it here. These are real sky images. That one without a star, you see this noise here. And if you look at this image where we have a star in that area here, the star image looks indeed blurred in that direction, which this blurring is not from the star signal itself, but stems from all these error contributors of the image sensor. Furthermore, these disturbances have the property to depend significantly on temperature, and also they increase over time, mostly during radiation. And as you can imagine, these disturbances can lead to a significant decrease in measurement performance if not handled well. So one possible solution to that problem could be to have a characterization campaign from time to time where you create a map of all the pixel characteristics. Well, our image sensor has 1K by 1K pixels. Then we need to characterize each of these pixels and put in some 32-bit floating point value for that. So you would need 4 megabytes only for that characterization image. So it's quite a lot. Currently, we have just 2 megabytes of RAM built into the star tracker. Also, you would have to switch the star tracker to a non-operational status and to perform this calibration campaign. And then we're still looking into the celestial sphere. So in the image, we will not only have this noise and white spots, but also real stars. And this would have to be filtered out in some way. Or you would have to shift your optic systems and look at the black body or something like that. So we would have to introduce some movable parts in the star trackers, which we currently have any at all currently. With all the implications with respect to the mechanics of the star trackers, we would definitely want to avoid that. And furthermore, we cannot take into account this short-term changes, for instance, related to temperature, especially when you're on an Earth orbit where you have different exposure to the sun. The star tracker will heat up and then cool down again, and you have, with a comparatively high frequency, changes in that temperature, which you could not characterize in this way. And the last point, this one requires ground maintenance, which we would also like to avoid. So our solution in this case is to have an in-situ characterization of the star tracker. And this works as follows. The star tracker reads windows of 15 by 15 pixels around each star. We have 16 of these windows available, and large portions of these windows are just dark. You're looking in deep space in that part, and you have only the star image in the middle of that window. So these border pixels, which don't receive any signal from the star, can be used for local characterization of the star sensor. Then your spacecraft is slowly rotating, so the window will follow the star as it moves across the sensor plane, and that leads to new pixels coming into view. And so you can enlarge your information about that pixel characteristics with the information from these new border pixels. And at some point in time, you have a complete knowledge about the pixel characteristics for your window. And for those pixels who've moved out of the window, you can forget about them. You don't need that information any longer. And how it works, I'll show in this movie here. What you see on the left is the typical image we receive from the star sensor. This contains not only the star image here, but also this noise and pixel non-uniformity. This part here contains the image or the pixel characteristics for the current situation. And finally, on the right, you find the corrected image where we have already taken into account those pixel characteristics. In the top row, you have the assorted three-dimensional plot of that, so that's not different. It's just to have a different aspect in looking at that. So now everything begins. When you look at the trained image, you see that we have a white spot here which comes into view. The star moves into the direction of the white spot, and if you look at the image and at the lower right, this image is corrected. We don't see that white spot any longer. We have a similar situation in a few moments where we again have the star image moving across such a white spot, and you can have again a look at how it works here. So now the white spot has again reached the star image, or other way around, the star is moving across that white spot, and it's been fully corrected. You cannot see any disturbance from that. Compare, especially look at the two different three-dimensional plots there where you have this large column with the white spot and nothing, nearly nothing on the right-hand side. So the result of this, we just need a very small memory footprint because we just have to store the information for our 16 windows. That's 15 kilobyte, and compare that with a 4 megabyte, which would have to be used in the alternative solution. Again, this conserves PCB area, power consumption, and in the end also cost. It's in situ, so it's always up to date. You have no interruptions of your star tracker operation and don't need any ground maintenance. And if you look at these graphs, this is the measurement of just one of the stars. In red, you can see how the measured star coordinates are pulled away from the exact position here. That goes up to 2 pixels here, and the dark graph here is the corrected star position, which only has very low noise around that correct position. And this is finally a plot of one of the axes of the complete attitude solution, where you also see how this filtering mechanism works. This is the situation in which we don't apply that filter, and this is the situation where the filter is active, and the scaling is the same on the two graphs, so you see how good it works. So that was all for me. Are there any questions? There's one.
Oh. Questions? Yes. Gail.
Hi, back on slide 12, I want to make sure I understand. You've got 4 copies of your code. You've got the bootloader, and also in PROM you have something called the recovery code, and then you have your actual operation code, and then you have a reference code. So you have 4 copies of?
In the end, there are 4 copies. 3, well, 2 of them should be identical. That is the double EEPROM image and the copy in the RAM. These are typically identical. Then we have the bootloader, which is just a small piece of code in PROM, and also the recovery application, which is also quite small compared to the nominal application.
So what's the reference code?
The reference code is we call it the reference image, which is created at cold boot time, where the bootloader copies the double EEPROM image to the RAM. This is the reference image, but you can also boot this reference image instead of the nominal boot process. So you can put a different application into that reference area in RAM, boot that before you actually modify the double EEPROM.
And can you load directly to RAM from the ground? Or do you have to load it into EEPROM and copy it over?
We don't support telecommands and telemetry while we are executing in PROM. So everything which does TMTC works from RAM. So either you boot the recovery application, where you can perform maintenance activity via TMTC, or you have the nominal application running, which also supports all these maintenance commands, and or as a third option, have the new copy in the reference image booted and do some communication as a first check before you actually modify anything.
Okay, thanks.
Hi.
Hi.
Question is what's the longest functioning star tracker that you have in space now? And the second part is, how long do you think the star tracker will last with all these different things you can do and uploading to take care of degradation in the camera?
If you ask with respect to any star tracker product of our company, that's for sure the predecessors, which are already flying in geo missions and have lifetime of more than 50 years per unit. Accumulated, I'm not sure. I wouldn't give any details because for sure these will be wrong. I don't know them by heart, the accumulated time. But for the ASTRO APS star tracker, there's one running since last year of July, end of July. We launched that, which is a demonstration payload on the AlphaSat telecommunication satellites, and it has been up and running since then. We had just one reboot during shortly after launch. This was traced back to a double bit error in RAM caused during the crossing of the radiation belts, and since then it's running without any problems. So the next star trackers of the ASTRO APS family will be launched beginning of next year.
Very good. Other questions?
So I'm trying to go through and understand the overall design. You have a RAM that has EDAC included.
Right.
And you've got EEPROM, which allows you to have some flexibility to alter your application.
Right.
The EEPROM doesn't have the EDAC built in.
It doesn't currently have the EDAC built in because we think it's not really necessary, as you don't execute. You don't need that on the fly correction mechanism which EDAC.
Right, and you've got software mechanisms to handle what the EDAC would do for you. Was there any consideration for other technologies? You're using an EEPROM, which is an older technology. Now there's MRAM and CRAM and a few other alternatives for non-volatile memory, or even flash, which has been flown now.
We've looked at least at flash and MRAM, and indeed there are some alternate concepts, hardware concepts, which use MRAM as an alternative to double EEPROM. Yes, but this MRAM usage is a bit different than the concept I've now presented here. I think that could be part of a talk next year or so to give more details on that.
Was the choice to use the EEPROM the availability of parts at the time? Did that factor into it, or was one of your issues really the printed circuit board space? The MRAM parts tend to be larger.
I think both. We didn't have that much experience with MRAM at that time, so we had double EEPROM before, not in flight units, but in some EQMs or just engineering models. So we were used to double EEPROM. We had that reprogramming software already in place. We just had to qualify that for flight model.
The other question I had, I'm not sure, I think you've presented it, but I wasn't clear on, your EEPROM allows you to have that flexibility if the EEPROM part becomes unavailable, or if the whole part fails. Is it still possible to run the star tracker by loading software directly into the RAM?
That's still possible. So if the double EEPROM completely fails, if the part is broken or something like that, the bootloader will detect some CRC, check some errors during booting, then start the recovery application. And using that recovery application, you can completely upload a new image to the RAM reference image. And after that, boot that reference image, and then you have your star tracker up and running again.
Very good.
Other questions? Nope. Yes? Okay, thank you.